So we are talking about differential equations, okay? And differential equations are not really scary. They just mean that we have an equation that has a dy dx in it, or a y prime, or something like that. Eventually, you will, if you continue with calculus, you will learn about situations where you've got y primes and y double primes, and really, that's not a weird thing. If you are in AP Physics, and even if you're not in AP Physics, you might remember an equation that looks like that. And you might remember that acceleration is kind of like the second derivative of position, okay? So it's really not all that weird. You're just not used to thinking about it that way, okay? So you were supposed to finish a problem for me, right? You were trying to solve f prime of x is equal to 2 over x cubed minus 3. Yes? No? Okay. And we were supposed to come up with an answer? All right. Somebody brave enough to give me their answer for f of x? Did anybody finish it? Fiona, be brave, please. No, I just want to know what f of x is equal to. Looks good to me. Okay, is that what other people got? You might have had your natural logs separated out. You might not have made them compact and put them into one thing, and that's okay. All right. Yes? No? How's it going? I see some nods, like, okay, we got it. Okay. Maybe if you can't get it, you need to come and find me. Okay. All right. So we're going to do one more example. That's kind of wacky. Actually, no, I don't want to do that first. Are there checkpoint questions? And then we'll do my wacky example. (4.1 to 4.6). Not all of them, because they didn't ask me to solve all of them. Checkpoint question. Dead. Checkpoint 4.6. So 4.6 says that v prime of t is equal to negative g. And we're supposed to find an expression for v. Okay. So what does v prime mean? What, Daggy? Yes, but how else would I write v prime? I guess is more what I'm going for here. By definition, that means like dv dt, right? Okay, is negative g. And then when we're solving a differential equation, the thing we usually do is bring our differentials on opposite sides. Okay. And then I integrate. And the antiderivative of v, of dv, excuse me, is going to be v. I've got this negative g, and the antiderivative of dt is t, but of course I have a plus c. And then I believe you have an initial condition, right? I think you know that it starts from S, so it tells you v0 of 0 is equal to 0. Okay, so I can use that initial condition to help me figure out what C is. Okay, remember that what we have right here, V is equal to negative GT plus C, is what we call the general solution, and what I often refer to as the family of solutions. Okay, and then we might have a condition, a point, that will help us pick out the particular solution that we're looking for out of this family. So I'm going to use my point, and that says that V is equal to 0 when T is equal to 0. So that tells me that C is equal to 0. So my answer then becomes V is equal to negative GT, or negative 9.8T, which should look familiar. Hang on, I have like error in my sorry. Yeah, and yours. What? Oh, okay. Well, I heard bird and I thought, oh my God, has something flown in? Because I can't deal with that right now. I mean, I could and I would, but like, I can't deal with that. My brain has already decided what we're going to do about it. But, all right, any other checkpoints? Okay, good. All right, then I want, like I said, to try one more, which is kind of wacky. So you are supposed to solve dy dx is equal to sine x squared. Okay. And we have the condition that y is equal to 5 when x is equal to 1. So again, and this, you have this example, right? It should be there. Okay. So again, if you're asked to solve a differential equation, basically you want to know y equals something. Okay. So the first thing that we're going to do is bring that dx over to the other side. And then we're going to integrate both sides. So you have come to an integral. Okay. Integral sine x squared dx. Can you solve that by inspection? Not really. Okay. How about you substitution? Well, what would you let u be equal to? X squared. Okay. So if we went over here and we let u be equal to x squared, du would be equal to what? 2x dx. And I don't have that x. Okay. So I can't really do that. What's next on my list? Integration by parts, but I don't really have two things multiplied by each other. Okay. Sometimes we do wacky things that way, but not today. And what's my last tool in my toolbox? Partial fraction decomposition, but I don't really have a numerator and a denominator. Okay. So I'm kind of stumped. But let's back up a little bit. And let's talk about the fundamental theorem of calculus, okay? Which is there for a reason. And the fundamental theorem of calculus says that df dx is equal to d by dx times the integral from a to x of f of t dt, and that's equal to f of x, little f of x. Okay. I don't know. Okay. So in our problem, df dx is equal to dy dx. A is equal to 1, and little f of x is sine x squared, right? And that comes from my initial equation up here and my condition about x equals 1. Okay, we good? All right. So this gives me, I rewrite the fundamental theorem of calculus. That gives me dy dx is equal to d by dx, the integral from 1 to x of sine t squared dt. Good. Everybody understand where all these pieces came from? That whatever I have out here is what I have inside the integral. It's just a function of t. Okay. So now I can take the antiderivative of both sides, right? Get rid of that d by dx. And this gives me y is equal to the integral from 1 to x sine t squared dt plus a constant. Because again, when I take the derivative, if there's a constant, it goes away, so I don't know what it is. It's ugly, okay? The answer has an integral in it, but that's okay. Sometimes that's just the way it works out, and that's why we're doing this example. Okay. But I can do something about the plus c, because I know, oops, that y is equal to 5 when x is equal to 1. Right? And then what's this? What's my integral from 1 to 1 of anything? 0. Thank you, Kim. Okay. So this tells me that 5 is equal to c. Or my solution is y is equal to integral from 1 to x sine of t squared dt plus. Okay, I just want you to see this so you don't freak out. Because freaking out is not good. You mean plus 5? I do mean plus 5. Thank you very much. I was concentrating so much on using up my extraneous dots and incorporating them into what I was writing. Diagonal.
So, before you substituted 5 and 1, where did the existing 1 come from?
Well, it came from the fact that I had an initial condition up here.
Okay, that's the thing.
Yes. Mm-hmm. Okay. So are we good with the basics of differential equations? Okay. Then let's move on to 4.2. If you downloaded the notes, oh, I don't know, before the Super Bowl yesterday, then you need to download them again because they were missing pictures. Because when I went through and organized all my notes, I realized I needed to scan some stuff. Okay, so you might need to download them again if you don't have a bunch of graphs in there. Okay. All right. So while differential equations are fun in and of themselves, we're really using them as a stepping stone to something else, which are called slope fields. Okay? And that is a way to draw the graph of a function using the differential equation and maybe not necessarily solving what the equation is. So the important thing to remember is that we all know that dy dx is equal to the slope at a given point, okay, at a given set of values for dy and dx. Okay. So we're going to start with this. Okay. And what we are supposed to do is match a bunch of functions. So function number 1 is dy dx is equal to sine x squared. You don't need to write this down in capital. Dy dx is sine x cubed. Number 3 is dy dx is cosine x squared. And number 4 is dy dx is cosine x cubed. Okay, so I have them in the right order. Do my numbers agree with your numbers? Yes, okay. All right. So we're supposed to match the differential equations. Those are the numbered things with the functions a through d. Okay. And remember that dy dx is what we're plotting there. Okay, and dy dx is the slope. So I love a good table. Okay, and maybe what we should do is use a table to organize our thoughts. Okay, and frequently when we're talking about slope fields, tables are useful. And because these are all trig functions, I probably want to think about things like 0, pi over 2, 3 pi over 2 pi, negative pi over 2, all that stuff. Okay, So let's make ourselves a table here. And what's going to be the values in my table are going to be dy dx is equal to the slope. And then I'm just going to have each of my different differential equations here. And then I'm going to take some values. So I'm going to have 0, pi over 2. I'm going to have pi, which is also equal to negative pi. And I'm going to have 3 pi over 2, which is also equal to negative pi over 2. So this is just going to tell us what the slopes are. And then we can refer back to our graph. Okay. So this is another one of those reasons why you have to know the sine and cosine of 0, 90, 180, 270, 260, -90, -180. Okay. So what is the sine of 0? So 0 squared is 0, 0 cubed is 0. What is the cosine of 0? 1 cubed squared is 1, 1 cubed is 1. Okay. What is the sine of pi over 2? 1, so 1 squared is 1, 1 cubed is 1. What is the cosine of pi over 2? 0 squared is 0, 0 cubed is 0. What is the sine of pi? 0, 0 squared is 0, 0 cubed is 0. What is the cosine of pi? Negative 1 squared is, negative 1 cubed is negative 1. Okay. The sine of 3 pi over 2 or negative pi over 2 is what? Negative 1. So negative 1 squared is, negative 1 cubed is. The cosine of 3 pi over 2 or negative pi over 2 is 0 squared is 0, 0 cubed is 0. Okay. So we might want to start by looking at the origin. Okay. So my first two functions here, sine x squared and sine x cubed, both have a slope of 0 at the origin. What does the slope of 0 look like? It's a horizontal line, right? Okay, so let's look back at our pictures here. Which of my graphs here have a slope of 0, have a horizontal tangent line at the origin? C, is that the only one? What? B, okay. So these could be B or C. My other two graphs, cosine x squared and cosine x cubed, all have a slope of 1, a positive slope of 1. Okay. So again, if we look back, we can see that A and D both have positive slopes. That's the slope of 1. Right behind that. Okay. So these are going to be A or D. So now, everybody good with where we are so far? So if this was a multiple choice test, we've already got a 50-50 shot of getting it right. Okay. So now let's look at what happens on either side of the origin. Okay. So for sine squared x, negative pi over 2 has a positive slope of 1, and pi over 2 has a positive slope of 1. So basically what I want is I want my slopes to keep being positive. And if you think about it, that makes sense. Because no matter what the sign of x is between -1 and 1, it's going to be positive because it's squaring. Okay? So if we look back at our choices of B and C, which one always has the positive slopes? Okay? So B is going to be number 1. Which should make number 2 C, but let's just talk about it for a minute. Okay. So if we go from negative pi over 2, which has a slope of -1, to pi over 2, which has a slope of 1, I want my slope to change. Okay. So if we go back and look at C, I have a negative slope over here and a positive slope over here. So that kind of makes sense that it's going to be C. And we can do a similar analysis for A and D. Okay. So again, if we look at one side or the other of the origin, okay, we find for cosine squared x that we're always going to have a positive slope. Okay. So if we go back and look and compare A and D, A always has positive slopes. So number 3 is going to be A. And then, if we look at number 4, we see we have this if we look at cosine x cubed, we see that we have these negative slopes. Oops, okay, so that is why am I feeling wacky about it? Well, because here's going to be my negative slope, and here's going to be my negative slope. Okay. All right. Make sense? Okay. I'm not going to ask you, and the AP exam isn't going to ask you to draw an entire slope field, which is why I said the comments I made in the journal outline guidelines, because that's just a lot of work to like make all of the dots and stuff. That's not how we can handle it. You may be given some fields and asked to produce things, asked to analyze them, but you're not going to be asked to draw all those pictures that were in. Okay. All right, we okay? All right, so let's talk about flow fields. So fields in general are a difficult thing to wrap your head around because you can't actually see them. What I have found that works as a definition for a field of any kind is it's a set of instructions. And those instructions exist regardless of whether or not anything is there. So for instance, you are surrounded by at least two fields that I can think of right now that you move within all the time. Okay? One of them is a gravitational field. Okay? And that field exists, and that field says no matter where I put an object, if I drop it, the gravitational field says this is what you have. Okay? And the gravitational field says, well, if I'm higher up, the force is going to be less, the acceleration is going to be less. If I'm closer to the Earth, the gravitational force is going to be greater, the acceleration is going to be greater. But you live in this gravitational field, okay? The instructions for what to do if an object is at this point and let go, those instructions exist whether there's an object there or not. Okay? Can you think of another field you exist in all the time? How about, oh, you got one? A magnetic field, exactly. You live in a magnetic field all the time. Those magnetic field lines travel through your body, travel all over all the time. You only see it when you bring up a compass, and the needle of that compass lines up with magnetic north, right? But that instruction that says turn the needle this way is everywhere all around you all the time. Okay? So fields are weird. But in this case, when we're talking about math, we're talking about usually a two-dimensional field. But basically what exists there is the derivative at that point, the slope at that point. And what's another word or another phrase for derivative? Slope at slope. That's another phrase for derivative. Slope of the tangent line, what else? Especially if you think about it in terms of physics again, that like A is equal to dt. What does that mean? The change. Okay, so we often think of another way of thinking about derivative is the change, the instantaneous change. So when a particle comes and interacts at a particular point in that field, the slope field says this is how you change. This is what you do next. Okay. So let's try to make one on our own. Okay. So I think it's example 2. Is that what we're up to here? Thank you, Annabelle. Okay. So again, if we go here, so the problem says construct a slope field for the differential equation. Our differential equation is dy dx is equal to 2x minus y. Draw tiny segments through the 12 lattice points shown in the graph. Okay. So what you want to do, the first thing you want to remember is that dy dx is the slope of the line that you're going to sketch at each of those points. Okay. So what we do is at each point we substitute in the x and the y value into our equation, and we get a value for the slope. Okay. So once again, I think the best thing to do is to make a table. Okay. So again, the values we're putting into our table are dy dx. My x values, and I find this is the best way to do it, is kind of to put the values in as they are in the grid. So our x values go from -1 to 1. And then our y values are 2, 1, 0, and -1. Right. There are 12 grid points and 5, 10, 11 of you. Convenient. I'm going to put your name in a box. Figure out the slope of that box. And then we're going to fill them in. All right, everybody got their slope? With the exception of Kim. All right. Katie, what's your value? -1? Because it's -1, right?
Oh, yeah, so
+1. Okay. Fiona. Tia. Sophie. Annabelle. I'm plugging in 1 for x. So that gives me 2 times 1 minus 0. So that gives me 2. Lily. Lily says 1. I believe 1. Kim's not here. We'll come back. Dagny. Okay. Eva. What? 0? Yep. Yvette.
It's -4.
What is it?
-4.
-4. Not sure I believe -4.
Oh, it's -2.
Okay. There we go. Harvey.
0.
I believe 0, but Eva, I think you need to figure yours out again. And somebody needs to figure out Kim's in the middle. 0, 1. -1? Yep, I would believe that. Eva, did you try again? Well, so I have 2 times -1 gives me -2 gives me -4. There we go. Okay. So now we have our slopes at all of our points, and we're going to substitute them in. Okay. This does not have to be perfect, but a couple things to remember. You know what a slope of 0 looks like, so make sure that you do that right. You know the difference between positive slopes and negative slopes, so make sure you do that right. You could probably draw a slope of 1 very well, okay, because that's just a perfectly diagonal line, 45 degrees. If you have something like -4 and -3 as your slopes, make sure the -4 is steeper than the -3. Okay, we're looking for general trends and comparisons among the points as opposed to, I don't know, trying to get out a protractor and making it work. Okay, so for instance, I'm going to start with my 0s. So I know that at 1, 2, I have a 0, and I know that I've got a slope of 0 at the origin. Okay. And then I would probably go down this column, this x equals 1 column, okay? Because I know that I can make a slope of 1, and then I just know that as I go down, I need to make my slope steeper, okay? And you do your best. Okay. I would probably start at the bottom for my x equals 0 column because again, this is going to be 1. 0, 1 is going to be -1. I can probably draw that pretty well. And then this is going to be -2, so it's going to be steeper. And again, I would probably start at the bottom here for the x equals -1 because again, I know what a slope of -1 looks like, and then you just make them steeper and steeper as you go along. Okay, we all right? We good? Yes? Okay. All right. So, example 3. So example 3 again, I believe it's copy. So example 3 gives us a bunch of slope fields. There we go. It was a little blurry. There were some light issues. The forward-facing camera on my phone died, so I had to use my old phone. There were problems. So I have all these slope fields, and I know that I am trying to figure out which of those slope fields goes with dy dx is equal to negative y over x. Okay. So there are some things that you can think about. Anybody got any ideas of things that maybe we should think about? Kate, what do you think?
We can't divide by zero.
Okay, so there can't be any values at x equals 0. Okay. So that's going to be pretty much the y-axis. And so that actually eliminates, which I hadn't really thought of as a way of looking at it, but it pretty much eliminates everything except a and b, right? Oh, Katie, you're winning. I had like this whole great big like logic thing, and now we're going to do this in 2 steps, which is wonderful. I'm glad you thought about it that way. We're going to do it my way. Fun. Okay. All right, so everybody see that? That's for C, D, E, and F. There are little slope lines along the y-axis. Okay. Anybody think of anything else we can think about? Go ahead, Tia. Okay, so let's talk about that whole quadrant thing. Okay, that was one of the big ways I was going to go through this. Okay. So when in quadrant 1, when x and y are both positive, what do we know about the slope? It's going to be negative. It's going to be less than 0, so it's going to look like this. Okay. How about quadrant 2? What's dy dx going to be in quadrant 2? Positive. Okay, so it's going to look like that. Quadrant 3, where x and y are both negative. It's going to be negative, like Tia said. Okay, so it's going to look like this. And how about quadrant 4? Positive. So it's going to look like this. Copy. I wonder if I copied the wrong set of colors. I copied the wrong set of graphs. No wonder it doesn't make any sense. Oh. I don't want to do that. Because those go with a whole bunch of other things. Okay, so, well, what we're going to do is, I can't scan this right now because I don't have my full phone. We'll come back and deal with this tomorrow, okay? These notes, what we have said is fine. It's just we have the wrong set of graphs, okay? So we'll just fix it. Okay, so we'll just come back. Nothing we've done is wrong. Okay, next. And I think we've got time to do it. So I'm sorry. Is the other big idea in here is Euler's method. Okay? And Euler's method is a way to directly estimate a particular solution without graphing or solving the whole slope. So if you remember in Hidden Figures, okay, when Katherine Johnson has climbed up the ladder where there's the big chalkboard and she's trying to solve it, and she says, Euler's method. And she goes running back in her high heels. I love it every time she does it. It's ridiculous. She goes running back and she pulls her book off the shelf and she goes running back and she climbs up and sees the whole thing went down. Okay, this is what she's using. There are a number of techniques that we learn about that were developed before there were electronic computers. Okay, ways that we estimated things, ways that we calculated things when you had to do things either by hand or with a four-function calculator. Okay, so she was using this type of thing to get us to the moon. Okay? Now, you can read about Euler's method, as I'm sure you did, and you probably read through it and you were like, what? What? So I think the easiest way to go through it is to do an example. And again, some of the things that your book wanted you to do with it doesn't make sense with what the AP exam is going to want you to do. Okay. So what are we up to? Example 4 or example 3? Example 4. Okay. So example 4 says use Euler's method with increments of delta x is 0.1 to approximate the value of y when x is equal to 1.3. And our differential equation is dy dx is equal to x minus 1. And we know that y of 1 is equal to 2. So, once again, a table is a delightful way to organize yourself. Okay? So the whole thing with Euler's method is we start with a particular value, with a particular point. And I'm going to figure out what the slope is at that point. I'm going to write down how far I'm going to move over in x. And I'm going to calculate what that means in terms of a change in y. And then I'm going to write down my new point, which is x plus delta x, comma y plus delta y. And I'm going to do this as many times as I need to get to my new point. So my starting point is 1, 2, because that's the point that I know about. That's the point that I know is on my chart, because I'm given that point. Now, this differential equation is not that bad. You could solve this differential equation, right? I mean, it's pretty easy. But not all are that simple. And things are a lot more complicated when you're trying to, like, go to the root. Okay. So if x is equal to 1, what is dy dx equal to? 0. Right? Delta x is 0.1. Because I'm given that. You will be given that. You will be told this is the increment you should use. Okay. And then what's delta y going to be equal to? Okay, it's going to be dy dx, which is 0, times delta x. That's going to give me 0. And my new point is going to be x plus delta x, 1.1 times y plus delta y, 2 plus 0. And then that becomes my new point. So dy dx equal to x minus 1. 1.1 minus 1 gives me 0.1. My delta x is still 0.1, okay, because I move by the same amount every time. And now what's my delta y equal to? Okay, 0.01, which again, maybe you could or could not do in your head, but you could do it with a 4-function calculator. Okay, and then I add. So I've got 1.2, 2.01. And again, that becomes my new point. Okay. So what's dy dx going to be? 1.2 minus 1. What is it? 0.2. My delta x is still 0.1 because I'm moving over by the same amount every time. What's delta y? Okay, 0.02. And then I add. So I've got 1.3 y plus delta y, 2.03. And that's my answer. If I wanted to move to the left, I would let delta x be negative. So I think we should try an experiment. I've actually never done this, but it occurs to me to try. Let's see if we can solve this exactly and see how far off we are. Okay. So if I have dy dx is equal to x minus 1, the first thing I want to do is solve for y. So dy is going to be x minus 1 dx. I'm going to take the integral of both sides. So that's going to give me y is equal to x squared over 2 minus x plus c. And I know that when x is equal to 1, y is equal to 2. So that gives me 2 is equal to a half minus 1 plus c. So c is 5 halves. All right? I think so. So this gives me y is equal to x squared over 2 minus s plus 5 halves. Right? And then I want to know what y of 1.3 is. So that's going to give me 1.3 squared over 2 minus 1.3 plus 2.5. Like I said, I have no idea if this is going to work. So that gives me minus 3 plus 5. Not bad. What did you get? 2.045. That's not bad. I mean, it's not wonderful, but you know, it's close. How could you make it better? Yes, you would make the change in x smaller, and that would give you smaller steps, and it would make it more exact. Okay. All right. So tomorrow we will go back and finish the example that I have the wrong picture for. There is one more example to do. I was inspired by what was hanging in the TAC and made a Black History Month calculus integration review that you can do tomorrow, especially because we have that quiz coming up on Thursday. And that means that Wednesday we will do the next section in the book, and I don't have that ready yet, but I'll have it ready, I hope, by the end of the day. Okay? So you don't really have anything to do for tomorrow. All right, and the homework is due today, yes? Is it? Oh, I'm sorry, so what? The partial fraction homework, I didn't put a due date?
Oh, you did.
Due tomorrow, okay. But integration by parts was due today, yes. Cool. Then I will get that later. All right, so we good? Okie dokes. Then be on your way. Have a lovely day. Clean your desk. Bye, Yvette. See you tomorrow. Yes. Why don't you take your things with you or put them out? You can put them out in the hallway on the table if you want. And then, yeah, of course.